Quantum Photonics Integrated Design Center is a Department of Energy-funded Energy Frontier Research Center led by Purdue University, and it was established in 2024. And it has 17 total principal investigators, and besides Purdue, there are 8 different partner institutions. The mission is on realizing robust many-body entanglement using solid-state photonics platform, including solid-state quantum emitters as well as nanophotonic structures. One of the biggest challenge using solid-state materials in quantum photonics is that there are inherent inhomogeneity in these materials. You would also have challenge in making all these emitters coupled together. The other challenge is this idea called dephasing, which means that because of this quantum emitter, they are influenced by environmental factors. And so how to overcome these 2 main challenges, that has been a very long-lasting problem in quantum photonics.
We are using all our expertise to try to figure out how to use solid-state emitters to make the most coherent photons possible. The center brings together a lot of different expertise. So we have experts in HBN defects, diamond defects, organic molecules, 2D materials, quantum dots. We have experts in dielectric photonics. And then we also have theoretical collaborators. The goal in NanoFab is to construct an optical system that has an interaction with the quantum emitter that both collects the light and also strengthens the quantum transition that we are using to create the photon. The theory goes into the photonics design and also the interaction of the emitter with the environment. We do theoretical work to try to figure out the ideal sample and emitter to use for this, and then also how to engineer the nanophotonics around that emitter to enhance this purity.
Materials are foundation of everything. So no matter what fancy idea you have to make your structures. And what's more important is you have to make it practical, because you want it to become a technology. Critical point here is to manufacture the structure, and that's where nanofabrication comes in. We are talking about making and controlling the emission from quantum emitters. This would be, tiny structures in themselves, and then we are designing a structure around it to gain the ultimate control over this emission, which means that we are designing structures that have nanometer scale dimensions. And we are leveraging a fantastic clean room facility here at Purdue, Burke Nanotechnology Center, that provides us with this unique possibility to both design and to fabricate structures on the nanometer scale.
There's a lot of groundbreaking quantum photonics research happening in the center. 2 examples that I'm particularly excited about are DBT molecules in cavities, where we try to establish a new 2-level emitter that consists of organic molecules in a host material. And another very exciting directions is looking at many-body correlations in charged environments. So that's a polaron problem. It's a somewhat well-studied problem, but now we're looking at it from the optical point of view, trying to see how we can get nonlinearities out of a polaronic many-body system and really understand that system deeply, and then to maybe connect it to photonics down the line. So I think the center brings us closer to harnessing quantum entanglement in real-world applications because it brings together a strong group of people that can all at the same time work on various aspects of the same problem across different platforms.
Because I am specifically really interested in eventually going into the field that this center is focused on, it's an amazing opportunity for me. And I've had a lot of opportunities to work with many different professors, make new connections, and do different work with the students in the center, and that is all, I think, an opportunity that I wouldn't have really had if this center didn't exist. So being able to be a part of this project and this mission and this kind of large collaboration, and just having access to all of these people with all of this knowledge has been hugely beneficial for me. And I think it's going to be extremely beneficial down the line as well for preparing me for the things I want to do later in my career.
The first goal, I think, is to generate foundational knowledge we are necessary to advance solid-state quantum photonics. And second goal is to generate like these many photon, many emitter entangled states that are can be resources to use for quantum computing, communication, and measurements and sensing. The third goal is to train a diverse workforce in quantum photonics. So this includes, postdocs, graduate students, and undergraduate students. I think that it's necessary to have a large team effort to attack these multifaceted challenges. QuPIDC is kind of uniquely occupying that space.